Solve problems on optimization. Wire connecting poles. Problem 15. Two vertical poles, as shown in this picture, the leftmost pole is called PQ and the rightmost pole is called ST, are secured by a wire that goes from the point P, that's the top of the leftmost pole, to a point on the ground, the point R, and then proceeds to the top of the rightmost pole to the point S. Now we have to figure out where the wire has to hit the ground so that the distance of the wire is as short as possible. And our task is to show that the shortest length of such a wire occurs when the two angles indicated in the picture, θ1 and θ2, are the same. The solution is going to be somewhat technical. We need to introduce notations. Let h1 and h2 be the heights of the poles. h1 is the height of the pole with base at Q, and h2 is the height of the pole with base at T. Let d denote the distance between the poles. The quantities h1, h2, and d are constants. They do not change. The quantity that does change is a point R where the wire hits the ground. We have to find an optimal location for this point R so that the combined length of the wire is as short as possible. So we denote the distance of the point R from the point T by x. If that is x, then the distance of the point R from the point Q is d minus x, clearly by the definition of d. And the length of the segment of the wire connecting P to R is denoted by d1, and the length of the other segment of the wire connecting R to S is denoted by d2. Then the length of the wire is d1 plus d2. And d1 and d2 can be computed in terms of x and d and h1 and h2 by theorem of Pythagoras. So d1 is square root of h1 squared plus d minus x squared. That is the square root of the sum of the cathets of this leftmost right angle triangle in this picture. Likewise, d2 is square root of h2 squared plus x squared. And therefore the length of this wire is d1 plus d2, that is square root of h1 squared plus d minus x squared plus square root of the quantity h2 squared plus x squared. So this is the length of the wire. This length depends on the point x. So we differentiate the expression for this length. So we derive L of x, which is square root of h1 squared plus d minus x squared plus square root of h2 squared plus x squared. We differentiate that with respect to x. And we get, by using the chain rule, that the derivative of L prime of x equals 2 times d minus x times negative 1, and that divided by 2 times square root of h1 squared plus d minus x squared, plus 2 times x divided by 2 times square root of h2 squared plus x squared. The 2's cancel out in both fractional expressions. And the leftmost fractional expression is d minus x times negative 1. So that expression has a negative sign which carries outside. So we write this for convenience in the form where we first mention the rightmost term, and that becomes x divided by square root of h2 squared plus x squared, and then we have minus d minus x divided by h1 squared plus d minus x squared. We obtained a representation for the derivative of the length function L prime at x as a difference of two fractional expressions which both expressions had square root denominators. Combining these two fractional expressions into one, we get a fractional expression whose numerator is x times square root of h1 squared plus d minus x squared minus d minus x times square root of h2 squared plus x squared, and whose denominator is the product of the original denominators, that is square root of h1 squared plus d minus x squared times square root of h2 squared plus x squared. We have to find the critical points of the length function L. That is, we have to solve the equation L prime at x equals 0. And now for this expression that we now obtained for L prime, the denominator is always positive. This expression is 0 only if the numerator is 0. So the equation L prime at x equals 0 is now equivalent to saying that x times square root of h1 squared plus d minus x squared minus d minus x times square root of h2 squared plus x squared equals 0. We move the quantity minus d minus x times square root of h2 squared plus x squared from the left-hand side to the right-hand side, and we obtain that the equation L prime at x equals 0 is now equivalent to saying that x times square root of h1 squared plus d minus x squared equals d minus x times square root of h2 squared plus x squared. To solve this equation, we have to square both sides. So we solve it by squaring both sides, and we get then x squared times h1 squared plus d minus x squared equals d minus x squared times h2 squared plus x squared. So in order to find the critical points of the length function, we now have to solve the equation x squared times h1 squared plus d minus x squared equals d minus x squared times h2 squared plus x squared. To do that, we expand the brackets. So we first get from the left-hand side x squared times h1 squared plus x squared times d minus x squared equals h2 squared times d minus x squared plus x squared times d minus x squared. We observe that the quantity x squared times d minus x squared appears on both sides of this equation. Therefore, it cancels out, and the equation simplifies to x squared times h1 squared equals h2 squared times d minus x squared. To solve this equation, we expand the product d minus x squared, and we get x squared times h1 squared equals h2 squared times d squared minus 2 times d times x plus x squared. Then we move everything from the right-hand side to the left-hand side, and we also expand the product on the right-hand side. We get, after this moving, minus h2 squared times d squared plus 2 times d times h2 squared times x minus h2 squared times x squared plus x squared times h1 squared is 0. So this is the equation for the critical points of the length function, and this can be written in a more convenient form as h1 squared minus h2 squared, and that difference multiplied by x squared plus 2 times d times h2 squared times x minus h2 squared times d squared equals 0. This is an equation of degree 2 for x. So the equation for the critical points is now h1 squared minus h2 squared times x squared plus 2 times d times h2 squared times x minus h2 squared times d squared equals 0. Now, if h1 happens to be h2, that is, if the poles are of equal length, then this equation is actually of degree 1 and not of degree 2. And the equation becomes 2 times d times h2 squared times x minus h2 squared times d squared equals 0. This equation is easy to solve. We get x equals d over 2 as a solution. Therefore, if the poles have the same length, then the point R, which corresponds to this optimal value, lies in the middle of these poles. And this means that by symmetry, the angles theta 1 and theta 2 are the same. Now we have dealt with the situation where h1 equals h2. Now we assume that h1 is larger than h2. We make this assumption for computational convenience only. If h1 is less than h2, then we may simply revert the roles of h1 and h2 and perform the same computation. Now, if h1 is larger than h2, then h1 squared minus h2 squared is positive. And we may solve this quadratic equation that we obtained for the critical points of the length function. We get that solutions are x equals minus 2 times d times h2 squared plus or minus square root of 4 times d squared h2 to the fourth plus 4 times h1 squared minus h2 squared times d squared times h2 squared. And that expression divided by 2 times h1 squared minus h2 squared. This is what we obtained simply by straightforward mechanical use of the quadratic formula. Now we observe that simplification happens. Under the square root in the numerator we have 4 times d squared times h2 to the fourth. That cancels out with the term 4 times negative h2 squared times d squared times h2 squared. So these terms, when we expand the brackets under the square root, cancel out. And we are left with one term only, that is the term 4 times h1 squared times d squared times h2 squared under the square root. So the solutions are x equals minus 2 times d times h2 squared plus or minus square root of 4 times d squared h1 squared times h2 squared. And that divided by 2 times h1 squared minus h2 squared. This now of course simplifies because under the square root we have a perfect square. Square root of 4 times d squared h1 squared times h2 squared is simply 2 times d times h1 times h2. So we conclude that the solutions are, the critical points of the length function are minus 2 times d times h2 squared plus or minus 2 times d times h1 times h2, and that divided by 2 times h1 squared minus h2 squared. Now, if we would have a negative sign in the numerator, then the numerator would be negative. And since we assume that h1 is larger than h2, then the denominator h1 squared minus h2 squared term would be positive. And therefore, the negative sign for the square root corresponds to a negative critical point. But this cannot come into question because x measures distance. Therefore, the only solution corresponds to the positive sign of the square root. So if we choose negative sign for 2 times d times h1 times h2, then x would be negative, which is not possible. And therefore, the critical point is x equals minus 2 times d times h2 squared plus 2 times d times h1 times h2, and that divided by 2 times h1 squared minus h2 squared. The 2's cancel out, and we are left with minus d times h2 squared plus d times h1 times h2, and that can be factorized. And also the denominator can be factorized as well. So this becomes dh2 times h1 minus h2, and that divided by the factorization of h1 squared minus h2 squared, which is h1 plus h2 times h1 minus h2. Now the terms h1 minus h2 appear both in the numerator and the denominator, therefore they cancel out. And we find that the critical point is d times h2 divided by h1 plus h2. This is a critical point for the length function, and then we observe that this value of x minimizes the distance since the derivative of the length function takes a negative value at 0 and a positive value at x equals d, and therefore by the first derivative test this critical point is absolute minimum for the length function. So this value of x minimizes the length function, and this value of x was a positive solution to the equation x squared times h1 squared plus d minus x squared equals d minus x squared times h2 squared plus x squared. Next we use this equation to get the desired result. So we have established that the positive critical point of the length function is the absolute minimum value of the length function. This positive critical point was a positive solution for the equation x squared times h1 squared plus d minus x squared equals d minus x squared times h2 squared plus x squared. Now we do not need the actual value of this positive solution. We need to know only that it satisfies this equation, because the statement of this problem follows from this equation. Now this equation can be written as x squared times d minus x squared, and that multiplied by h1 divided by d minus x squared plus 1. That's the left-hand side. The right-hand side is d minus x squared times x squared times quantity h2 divided by x squared plus 1. Now this is a technical modification that we have done, expanding the brackets on the left and on the right-hand side of the second expression, second equation, we get the first equation, as can be easily and directly verified. Now the advantage is that since x is positive and less than d, x squared and d minus x squared are both positive numbers. Therefore they cancel out of this equation. So x squared, which appears on both sides, cancels out, and so does d minus x squared. So we are left with h1 divided by d minus x squared plus 1 equals h2 divided by x squared plus 1. And the ones which appear on both sides of the equation also cancel out. So this can be done since x is different from 0 and d different from x. And the equation simplifies to h1 divided by d minus x equals h2 divided by x. So we have established that the positive critical point, which is the absolute minimum value of the length function, satisfies the equation h1 divided by d minus x equals h2 divided by x. So from the figure we compute that tangent of theta 2, that is the rightmost right angle in this picture, is the vertical cassette h2 divided by the horizontal cassette x. So tangent of theta 2 equals h2 divided by x, and that is the right hand side of this equation, h1 divided by d minus x equals h2 divided by x. Tangent of theta 1, that is the tangent of the acute angle indicated here in this picture of the left right angle, is the vertical cassette h1 divided by the horizontal cassette d minus x. So tangent of theta 1 is h1 divided by d minus x, and that is the left hand side of the above equation. This above equation therefore means that tangent of theta 1 equals tangent of theta 2. And this, on the other hand, means that theta 1 equals theta 2. So we have shown the claim that the absolute minimum length that is obtained when theta 1 equals theta 2.